We are going to run this simple simulation manually. First, initialize the system. Next, pick an event from the calendar. Update the current simulation clock time and execute the processes with the event. Keep doing it until there's no more event left. This is also the way a computer handles the simulation. We can develop some insights by doing this simulation manually. Now let's consider the geopress problem in your textbook. The time unit must be consistent throughout the simulation. In this case, we assume it is in minutes. Here are the given date from the textbook example. We will manually simulate the process up to 15 minutes in this lecture. We have mentioned the pieces of simulation before briefly. Now let's look into them. First, entities are the players in a simulation. In the geopress model, the entities are the parts. In some cases, we may need to introduce some fake entities to help modeling. The first thing for building a model is to identify the entities. In this example, the entities are the parts. Entities must have attributes. The attribute values are usually different for each entity. For example, arrival time for each part is different. Arena has some built-in attributes for entities. We can add additional attributes for entities. In this example, the attributes for the parts include arrival time and surface time. Global variables describe something for the whole system. They are not tied to just one entity. The simulation clock is a global variable. It tells us the current time. Resources are what entities compete for. In the geopress problem, the geopress is a resource. Each part is processed by the geopress. Part is the entity. Geopress is the resource. Many systems have queues. In the geopress problem, there's one queue of parts. Queue may have limited length due to the buffer capacity. We explained that we always want to collect statistics to evaluate the performance. Arena is able to collect many statistics automatically. We can also specify what we want to collect. Here is a list of possible statistical accumulators for this simple system. We have explained all of them in the ice cream shop example. Let's again have an overview of the simulation dynamics. During the simulation, we change the entity attributes and the global variables based on events. When a new part arrives, we need to do a few things. First, we need to update statistical accumulators. We set the arrival time attribute of the part. We see if we can get the machine resource. We will then schedule the next arrival if necessary. When a surface is completed, the part leaves the system. Again, we need to update related statistical accumulator and other parameters. We also update the queue and resources. At the end of the system, we need to make conclusions by updating statistics. We introduce a few symbols that will be used in our manual simulation. We have an event calendar. We have state variables to indicate the server busy status, number of customers, and arrival time of customers in queue. B of T is for server status. Q of T is the number of customers. Here is the setup of our manual simulation. In the first line, we have a few variables and attributes. We use the yellow box to represent the dual press, the resource. In the second line, we have a few statistical accumulators. In the third line, we plot two graphs to help us visualize the progress of simulation. The last two lines are inter-arrival times and service times. Remember that inter-arrival time is the time between two adjacent parts or customers. Let's start. At t equal to 0, we initialize the variables and a statistical accumulator to 0. At time 0, we have the first part, and we will simulate up to t equal to 15 minutes. At time 0, the first part arrives and uses the dual press right away, as shown in the top left corner. We also plot Qt and Bt based on the inter-arrival time and the service times. We know that the next event is the arrival of the second part at t equal to 1.73. The event after will be departure of the first part at t equal to 2.90 when it finishes processing. At t equal to 1.73, part 2 arrives. Since the dual press is still busy with the part 1, the part 2 has to wait in the queue. We update the variables, attributes, statistical accumulators, and the graph. We also update the event calendar by adding another event, that is, the arrival of the part 3. Its arrival time is 1.73 plus 1.35 equal to 3.08. At t equal to 2.9, another event happens. Part 1 finishes and leaves the dual press, and part 2 immediately grabs the dual press. We continue to update the variables, attributes, statistical accumulators, and a graph. We also update the event calendar by adding another event, that is, the departure of part 2. Its departure time is 2.9 plus 1.76 equal to 4.66. At t equal to 3.08, another event happens. Part 3 arrives, and since part 2 is still being processed, part 3 has to wait in the queue. We continue to update the variables, attributes, statistical accumulators, and the graph. We also update the event calendar by adding another event, that is, the arrival of part 4. Its arrival time is 3.79. Actually, we should have added this event in the last slide since 3.79 is before 4.66, the departure time of part 2. At t equal to 3.79, another event happens. Part 4 arrives, and since part 2 is still being processed, both part 3 and part 4 have to wait in the queue. We continue to update the variables, attributes, statistical accumulators, and the graph. We also update the event calendar by adding another event, that is, the arrival of part 5. Its arrival time is 4.41. Actually, we should have added this event in the earlier slide since 4.41 is still before 4.66, the departure time of part 2. At t equal to 4.41, another event happens. Part 5 arrives, and since part 2 is still being processed, parts 3, 4, and 5 will wait in the queue. We continue to update the variables, attributes, and statistical accumulators and the graph. We also update the event calendar by adding another event, that is, the arrival of part 6. Its arrival time is 18.69. This will be after the simulation ends. At t equal to 4.66, another event happens. Part 2 finally finishes, and part 3 starts being processed. Parts 4 and 5 continue to wait in the queue. We continue to update the variables, attributes, statistical accumulators, and the graph. We also update the event calendar by adding another event, that is, the departure of part 3. its departure time is 8.05. At t equal to 8.05, part 3 finishes and part 4 starts being processed. Part 5 continues to wait in the queue. We continue to update the variables, attributes, statistical accumulators, and the graph. We also update the event calendar by adding another event, that is, the departure of part 4. Its departure time is 12.57. At t equal to 12.57, part 4 finishes and part 5 starts being processed. We continue to update the variables, attributes, statistical accumulators, and the graph. We also update the event calendar by adding another event, that is, the departure of part 5. Its departure time is 17:03. This is after the simulation ends. At t equal to 15, the simulation ends and part 5 is still being processed. We continue to update the variables, attributes, statistical accumulators, and the graph. We no longer add events since the simulation has finished. In the end of the simulation, we can collect the final statistical accumulators. We have discussed this earlier, and this is similar to the results of the ice cream shop problem. Please spend some time in reviewing these slides.